Okay, hi everyone. My name is Sam Silvestro. Today I'll be presenting Garter, a tunable secure allocator. This work was a collaboration with my lab mates Hongyu Liu and Tianyi Liu, as well as Dr. Lin of Ohio State University and my advisor, Dr. Tongping Liu. So I'll start by briefly re-summarizing some of the common heap vulnerabilities. So first we have buffer overread, which can result in information leakage. This occurs when the length of a read goes beyond the end of an object. A good example of this problem is the heartbleed vulnerability in OpenSSL that was discovered a few years ago, which affected millions of users' private information. Next is use after free. As the name implies, this occurs when an application frees an object but then continues to use it. Buffer overflow, I'm sure you're familiar with the stack-based buffer overflow. And on the heap, it looks very similar, except the attacker may be looking for something like a function pointer in a structure that's allocated to the heap that they can attack. And then finally, double free refers to when a heap object is freed more than once, and an invalid free occurs when an address not associated with the valid heap object is passed into the deallocation functions. Now, these last three can produce unexpected results, anything from a program crash to hijacked control flow. So to show where we are with these vulnerabilities right now, you can see the number of occurrences for each of these in just the past year, according to NIST's National Vulnerabilities Database. Not surprisingly, buffer overflows top the list, but interestingly, use after free is in the runner-up spot. And a recent study showed that use after free errors are the most severe vulnerabilities of the Chromium browser in terms of both the number of occurrences and the severity of security impacts. Typically, though, the memory allocator forms the front line of defense against these vulnerabilities. However, the Linux allocator doesn't provide any security guarantee. Because of this, we have several secure allocators that were designed to alleviate these problems, each with a varying level of security. So first, we should talk about the default Linux allocator and why we need secure allocators. The Linux allocator was designed to perform well as a general-purpose allocator and combines bump pointers and free lists to manage heap objects. So a free list is simply a linked list of deallocated objects, and a bump pointer points to the top of the heap, which represents the next unused portion of the heap. So I have a simple example here of a bump pointer modeled after the Linux allocator. And you can see that this state represents the bump pointer immediately prior to an allocation request. And this is after. So you can see this is a very fast and simple mechanism. But the problem is that the default Linux allocator wasn't designed for security purposes. And one of the issues is that it prepends metadata before actual heap objects. So you can see from this illustration, the metadata contains the previous object size as well as the current object size. And there's also some status bits embedded in there, which I omitted just for clarity. And in the free space, it stores its free list pointers. It typically uses doubly linked free lists, which is why there's a forward and backward pointer there. But you can see a problem if an overflow occurs. It can not only crash the size and status metadata, but it can manipulate those free list pointers, which can give the attacker some control over the allocation functions. Also, it provides no randomization, which makes it easy for an attacker to determine which objects will come up for reuse next. And then lastly, it has poor handling of double and invalid frees. So as an example, if the metadata were crashed, the allocator is unable to check the object status, which can lead to the same object being utilized more than once, and could ultimately result in hijacked control flow. So as you can see here, the default Linux allocator can't provide a good defense, which is why we have secure allocators, which are designed to improve the situation. Now, a few of these existing allocators are the OpenBSD allocator, DieHard, and FreeGuard. Now, each of these allocators are known as bibop-style allocators, right, which was mentioned, due to their choice of memory layout. Bibop standing for big bag of pages, in which a bag is just a collection of pages that store objects of the same size class. So for example, we might have a bag for 16-byte objects, a bag for 32-byte objects, 64, and so on. In addition to bibop, they also segregate metadata away from the actual heap, which helps mitigate against metadata-based attacks. Now, each of these allocators also feature randomization. For example, DieHard has log n bits of entropy, where n is the number of free objects in a given size class. OpenBSD ranges from 2 to 10, depending on the particular size class, and FreeGuard has a constant 2 bits, which is the same across all the size classes. Now, as an aside, each of these allocators offer many good security features, but OpenBSD and DieHard in particular can also experience high performance overhead. So as you can see, OpenBSD had an average runtime overhead of 31% in our evaluation, and DieHard measured 74%, but actually showed up to 9 times in the worst case. So after analyzing the allocation entropy for each of these allocators, you can see the problem visualized in this chart. First, they each either exhibit low entropy, like FreeGuard with its constant 2 bits, or unstable entropy, like OpenBSD and DieHard, where the entropy starts to drop precipitously as we move toward larger and larger size classes. So let's look at DieHard. DieHard always chooses one object from among all the available objects in the size class. However, the bags hold fewer and fewer objects as we increase the size of the objects in them. So unfortunately, this means the allocation entropy will decrease across the size classes, like we saw. Also, it can take a very long time to perform the search for an available object, because there can be a high probability you'll select an object that's already in use. So we can end up repeating this process of random checking over and over again. And finally, its security is bound to its specific design, which means it's not flexible. So this leads us to the motivation for an allocator that's designed to be both reliable and tunable. So for an allocator to offer reliable security, we would like it to provide stable randomization entropy across all size classes, inputs, execution phases, and applications. This would mean that the user should be able to precisely specify a lower bound for the entropy, and the allocator will guarantee to provide at least this minimum level of security. Also, tunable security refers to the allocator's ability to be adjustable based on the user's particular performance budget and their security needs. So if I use 10 bits and the memory overhead is too large, then the tunability will allow me to tailor my security to my particular environment. So to achieve these goals, we need to talk about how we can achieve a specific level of entropy. So a basic approach to this problem might be to simply use an array of a particular size, which will act as an object buffer. For example, if we populated this array with 256 objects, then randomly choosing one from amongst them would give us 8 bits of entropy. Of course, this introduces a couple of challenges. First, how do we handle deallocations? More specifically, how do we avoid searching for a position in the buffer in which to place the freed object? Secondly, how do we avoid the issue of excessive random check cycles when trying to find an available object in the buffer? And thirdly, how do we provide a stable level of entropy without being required to repopulate the buffer after every allocation? Because in this example, we would need to maintain that full set of 256 objects. So in order to address the first issue concerning handling deallocations, Garter maintains a separate deallocation buffer. Every thread has a pair of allocation and deallocation buffers for each size class. So for example, in a particular thread, the 16-byte size class has a pair of buffers, so does the 32-byte class, and so on. So this deallocation buffer gives us the ability to provide constant time deallocations in the common case because we manage it as a circular buffer, and the newly freed objects just inserted at the head. The second challenge was how to provide a minimum E bits of user specified entropy without being required to refill the allocation buffer after every satisfied allocation request. So for this, we use a buffer that's twice the size necessary to accommodate E bits. So in other words, we have a buffer capacity of 2 to the E plus 1 objects, and we ensure that we never fall below half that level. And the last challenge concerned how we would avoid excessive checking cycles during allocations due to that probability of choosing an empty slot in the allocation buffer, which of course, as more and more objects are consumed and taken out of the buffer, the likelihood of that happening increases. For this, we divide the allocation buffer into 8 regions, so we can test each region as a whole unit without having to check each and every object inside of it. Also, when we do end up selecting an empty slot, rather than just continuing to try random choices indefinitely, we perform a forward walk from the current location. And you can see from the diagram that the allocation buffer will perform its filling step from either the deallocation buffer or the top of the heap, if not enough read objects are available. So this design actually allows us to provide both tunable heap overprovisioning and random guard pages too, which we'll talk about next. So heap overprovisioning is an allocator feature where some portion of the heap objects are dedicated to never being used. The idea here is to interleave this unused space among the normal heap data. So if an overflow were to occur, hopefully it would be contained within one of these adjacent unused objects. The design of Garder's allocation buffer lends itself for allowing for tunable overprovisioning. When the allocation buffer falls below half full, it will initiate that filling step, at which point Garder will randomly select 1 out of 8 new objects positioned at the top of the heap and skip them, which will cause them to never be used. The remaining 7 out of 8 objects will be used for the filling operation. Now this figure is actually a simplification of how Garder actually performs the overprovisioning, but we reduce the number of random operations required by 7/8 compared to the naive method of just computing probabilities for each of these objects. If you're interested in the specifics of the implementation, it's explained in section 4.2 of the paper. So the allocation buffer design also allows us to provide tunable random guard pages. And a guard page is just like a regular page in memory, except it has all of its protection bits turned off. So any attempt to read, write, or execute on it will trigger a seg fault, and the program will crash. Garder uses static guard pages too, which are placed at the end of every bag. But it also provides a tunable proportion of random guard pages, which get distributed throughout the bag. We use a default proportion of 10%. So by default, 10% of the heap's address space will be dedicated to these random guard pages. And I mention address space because guard pages aren't backed by physical memory. So this isn't increasing the memory footprint of the application. Obviously, this will help protect against things like buffer overflow and heap spraying attacks, because if an overflow were to touch one of the guard pages, it will cause a seg fault, and the program will crash or halt right there. Here you can see our runtime performance. So we evaluated Garder with 21 applications, including the Parsec multi-threaded benchmark suite, as well as 8 real-world applications. All of these values here have been normalized to glibc, so anything less than 1 is faster than the default Linux allocator. And as you can see, on average, Garder is faster than DieHard and OpenBSD, and is essentially tied with FreeGuard. So FreeGuard has less than 2% overhead on average, and Garder has less than 3% on average, but with the much stronger security guarantee. So why is that? Well, there's 2 primary reasons why Garder performs better than other secure allocators like OpenBSD and DieHard. First, Garder avoids the use of a central lock, with the exception of a global free cache that's used under certain memory access patterns like producer-consumer. The other allocators have to acquire a lock on allocation and deallocation. And the second reason can be seen in the table, which shows the number of trials needed to perform each operation for these allocators. You can see that while Garder has a larger maximum for allocations, it also has a smaller average. Also due to the design of the deallocation buffer, we have constant time single trial deallocations. And this data was collected with Garder's default tunable parameter of 9 bits of entropy. Here we can see a comparison of the security features that are implemented among these allocators. Garder provides the most complete feature set with respect to these works and provides the strongest guarantee in terms of randomization entropy. You can see that Garder also implements fully segregated metadata, canary checking on free, and can detect all double and invalid frees. So now that we've seen an overview of Garder's allocation and deallocation buffers, let's take a look again at the entropy data, but with Garder included. So you can see here that Garter shows stable entropy across each size class. Like I said, for this evaluation, Garter was configured with 9 bits of entropy, and the average overall value was 9.9, because of course 9 bits would be the bare minimum that it would guarantee. In actuality, it came out much closer to 1 more bit, because it has twice the number of required objects to maintain the 9 bits. So why does tunability matter? Here we can see the results when we use different tunable factors. Whenever we use parameters that introduce higher security, of course that usually indicates higher overhead. If we use higher entropy, the memory overhead is actually significantly higher. The table here is showing performance. And all of these values have been normalized to Garter's default settings. So like I said, 9 bits is the default entropy parameter. 1/8 overprovisioning factor is the default, and 10% guard page proportion. So overall, this is Garter's position with regard to the allocators we've discussed. On one side, DieHard features strong security, but has the worst performance overhead. And on the other extreme, we have the Linux allocator, which performs very well, but has no security guarantee. In terms of both performance and security aspects, Garter provides the best combination of them both. Which leads me to conclude by saying tunable security allows users to choose their security level based on the performance budget. Reliable security provides a stable entropy level across size classes, inputs, execution phases, and applications. The allocation buffer design facilitates other tunable features like the heap overprovisioning and random guard pages. And Garter implements the greatest feature set compared to the other evaluated allocators, all with less than 3% performance overhead on average. So with that, I'll take questions. Thank you.
Thanks for the talk. When we start to introduce tunability, we start to increase mental cognitive overhead required on the developers. Did you do any research into understanding how users might use these features, whether or not they might actually not understand the implications and tune against or for security because they want better performance? The question is really like, is tunability versus a static set of features worth the cognitive overhead and possible failure of developers?
Yeah, that's a really interesting angle and question. No, I definitely haven't considered that, or that was kind of outside the scope of what we looked at. But no, that's a very interesting point, and probably warrants some research.
Thank you.
Yeah, thank you.
Really interesting work. My question is actually very similar to the previous gentleman. May I have a suggestion, though? Because we build secure systems, we always can come up with a chart saying security here, performance here, see we're there, right, better than everybody else. Right. Can the community challenge ourselves, putting another dimension, saying usability, adoption? I can tell you my system here is great. Usability is the lowest because it's more complicated and so forth. Just a suggestion, challenge for the whole community. If we want to make anything this is useful, we have to think about that angle. Thank you.
Yeah, thank you.
Hello, I'm Taesu Kim from Georgia Tech. I actually have 2 questions for you.
Sure.
The first one is, isn't it a little bit unfair to say that having larger entropy, in particular in the heap space, having better security, for instance? Windows 10 introduced a heap allocator that have randomness in their implementation, but in many cases, deterministic behavior of the application and heap layout sometimes prohibits some of the exploitation.
Right.
And thanks to your randomness that you introduced from the library,
right,
sometimes exploitation becomes possible. Right? What do you think about this kind of problem that you introduced from your allocator? That's the first question.
Yeah, that's that's true, right? So the increased randomization is a tool that may or may not necessarily mean anything if the application has other problems. I think is that what you're saying?
Okay. Second question is most of the heap allocator is optimized for reducing fragmentation. That's directly related to their performance goal. But it seems most of your performance benefit directly come from per core allocation behavior, which is a little bit unfair to compare against the other heap allocator that you evaluated. These guys do not care about this per thread behavior. But the reason that you introduced the per core allocator and deallocator list, perhaps, I think that's the only direct, I would say, performance benefit, right? Do you have any number for the fragmentation?
No.
Okay.
Hi, great talk. Sean Heelan, University of Oxford. One of the questions I often have when people talk about secure allocators is, say, what are the known limitations, say, at the time of presentation? Like, have you sat down and tried to write an exploit with Garter as like, say, the system allocator? And if so, have you any thoughts on what the limitations might be, or what would you do next?
Yeah, actually, in the paper, we use several real-world bugs to evaluate Garter. Yeah, so those details are actually in there if you're interested in those. But obviously, I hadn't included those in the talk.
Okay. I guess my question is more: have you then sat down and tried to actually defeat Garter, like purposely, as opposed to taking existing exploits and running them?
Oh, I see what you're saying. No,
yeah.
No.
Okay, cool. Thank you.
Yeah, sure.
All right, we are right about on time to finish this session. Let's just give one more round of applause to the speakers.